So before continuing with the next talk, I would like to make an announcement. So we have the place for the next school, for the next president school. It's going to be in Salvador, in Federal University of Bahia. So we already decided the dates also. It's from 25 to 29 of October, in 2 years from now. So here it's Elais from Bahia also. She will be in the organizing committee. So, so we are really happy with this decision. We were expecting this for a long time, so everyone is welcome, okay? So I expect in 1 year maybe you will hear from the event, but you can mark already in your schedule, okay? So now let me introduce the next speaker. So you can change this. So now Marcelo Viana is going to talk. He's going to give a tribute to Jacob Palis. So thank you, Marcelo.
Thank you for the invitation. It's working now? Yeah. So thank you very much for the invitation. I understand that we already had a lecture on Monday by Lorenzo about Jacob's impact in dynamical systems. We prepared the lectures completely independently, and then we exchanged the results. So I know what, I couldn't attend, but I know what Lorenzo spoke about. My lecture will have some intersection, but there's also quite a bit of complementarity between the two. So a few personal informations about Jaco. He was born in Uberaba, Minas Gerais, on March 15th, 1940. Came to Rio to enroll in the School of Engineering of what was then called the University of Brazil, UFRGS, where he graduated in 1962. Short afterwards, he moved to the United States to have a PhD with Steve Smale. Initially, he was planning to go to Chicago, but more or less immediately, Steve Smale moved to Berkeley, so Jaco went along with him. And he graduated with a thesis on Morse-Smale diffeomorphisms, and I will come back to the content of the thesis in a little while, in 1968. And then he made a very strange decision. He had a career in the United States ahead of him, and instead he decided to come back to Brazil, which, if you think about it, was really a very strange thing to do. Brazil had very, very little to offer in terms of incentives to a brilliant young scientist back then. CNPq existed, but had no budget. There were no grants. There were no research projects. When nowadays we complain that the budget for science is small, we should think of what the reality was back then. And still, Jaco decided to come. And I remember Mike Schub, who was a colleague of Jaco's in graduate school, saying, Jaco was different in that he knew what he wanted to do. We were all young people who liked math, but had no plans for the future. And Jaco, he knew what he wanted to do. He wanted to come back to Brazil and develop mathematics in the country. So he came back. He joined IMPA in 1969. IMPA was not this back then. It was located in Botafogo in a very small headquarters, and he became a researcher here, where he stayed for the whole of his career. He retired in 2015, and immediately was elected an emeritus researcher of IMPA. And he was the director from 1993 to 2013. So for 10 years, he was the director here. If you search the Math Genealogy Project, you'll see that Jaco had 41 PhD students from various countries. And when I checked this, which was some time ago, he had a total of 347 academic descendants, but that's probably already has probably already increased. He published in a total, according to MathSciNet, a total of 74 research publications in such journals as the Annals of Mathematics, Publications Mathématiques Liégeoises, Acta Mathematica, Invenciones Mathematicae. Has a long list of co-authors, but his favorite co-authors were definitely Sheldon Newhouse, who was also a colleague in graduate school, and then Forrest Stakens from the Netherlands, and especially Jean-Christophe Yocos, with whom he wrote several papers. 25 years ago, we had a conference here in this, at IMPA, in this auditorium, celebrating Jacob's 60th birthday. I organized the conference, and I asked Sheldon Newhouse to do what I'm doing now, to talk about the work of Jacob. And Sheldon gave a beautiful lecture, did a very good job, but I don't think he was prepared to the magnitude of the task. By the end of the lecture, he had been able to speak about 1/2 of what he had prepared. And I thought that was a pity. Especially it was a pity that the lecture would be lost. Fortunately, we had started recording lectures here. And so I asked the graduate student to go through the video of the lecture and transcribe it into a written form. Then I revised it, and I offered it to Sheldon. I revised it, and I increased it. I expanded the text to complement the parts that Sheldon had not been able to talk about. And the result is this paper, which appeared in Asterisk in the year 2003 by Sheldon. This is the table of contents, and it's an overview of what Jacob had done up to then in the vision of Sheldon, with some additions by us. I'm not going to repeat Sheldon's mistake and try to go through all of it. I will pick 3 of those sections, and I will try to explain what is the mathematical content behind those titles. So I will highlight especially the section about global stability, which was where Jacob's thesis belongs. Then the long-term project that he engaged in right afterwards in bifurcation theory, especially with Sheldon and Flores. And then the third part will be about a global view of dynamics, the kind of scientific interest that Jacob got passionate about in the 1990s and following, when he formulated various conjectures trying to rescue some image of what a typical dynamical system looks like. So global stability. A little bit of formalism. We are going to look at either diffeomorphisms of vector fields on a compact manifold. The corresponding spaces have a topology, the CR topology. And in 1937, Andronov and Potriagin had introduced, they call this robustness, coarseness, a coarse system. We now call it structurally stable. So it means structural stability means a particular dynamical system is structurally stable if any one which is in a neighborhood in the space of all dynamical systems is conjugate to the initial one. So if for every nearby G, there exists a conjugacy between the dynamics of the two systems. So structural stability means that changing the dynamical system slightly does not change its dynamical behavior. You get an equivalent dynamical behavior, where equivalence means up to this conjugacy. And there are similar definitions with some caveats, similar definitions for vector fields. So Pontryagin and Andronov introduced this notion, but there were no theorems about this notion. And legend goes that in 1953, Peixoto was at IMPA's library, had just received a package of books and journals. That's 1953. IMPA had been founded in 1952. So the library was already pretty good, and they received publications. And he went through one of the journals, and he found an article about this notion of structural stability, got interested in it, and started to work, and eventually proved this theorem, which is the first main theorem in this direction. You look at the space, the subset of all vector fields on an orientable surface, so 2 dimensions, orientable surface, and you assume that the system satisfies 3 conditions: finitely many critical elements, which means either periodic solutions or stationary solutions, so there are finitely many of those. There are no settled connections between the stationary solutions, and the alpha and omega limit sets of any point consists of 1 critical element. And this, I think, was very vaguely called gradient type vector fields. And Peixoto proved that every one of them is structurally stable, and moreover, that the set of all of these gradient-like vector fields is an open and dense subset of the whole space. So every vector field on an orientable surface can be approximated by one that is structurally stable, and the structurally stable ones contain an open and dense subset of the space of all dynamical systems. This was the very first big theorem in structural stability in this direction. And Smale, who visited IMPA at the end of 1959, during the first half of 1960, Smale was here working on the Poincare conjecture, but he heard Peixoto talking about these things, got interested, and he tried to generalize the theorem of Peixoto, the theory, by introducing a class of either vector fields or diffeomorphisms on any manifold. The main point of the generalization was to go from 2 dimensions to any dimension, and to introduce a class of systems inspired by the gradient-like systems of Peixoto. And Tom called Smale's class of systems Morse-Smale, and Steve conjectured that every Morse-Smale system is structurally stable, and the set of Morse-Smale systems is open and dense on the space of dynamical systems, either vector fields or diffeomorphisms on any manifold. So in other words, the conjecture is what Peixoto proved for orientable surfaces should be true for any space. Peixoto proved for vector fields on surfaces should be true for on any manifold. In fact, the second part, the part of the second conjecture, the density, is false, and I will come back to that in a little while. The rest of this conjecture was Jacob's thesis. He proved that for any compact manifold, Morse-Smale systems, either continuous time or discrete time, are structurally stable, and they form a non-empty open subset of the space of all systems. And this was the first time it was proved that any manifold can carry structurally stable systems. There were very few examples. This is the first time that it was known that on any manifold there are Andronov-Pontryagin type of dynamical systems. Just a couple of sentences about the proof. Jacob first proved it in 2 dimensions, and the idea was you look at the critical elements, say at the fixed points, saddle type fixed points, and it is known that in the neighborhood the system can be conjugated to a linear map, that the system is linearizable, and that's the Hartman-Grobman theorem. So on the vicinity of every critical element, there are coordinates that conjugate the different systems. And the difficulty is to go from the neighborhood of these critical elements to the whole manifold. You'll do that by following stable and unstable manifolds, and you have to worry with the place where they start to interact, as the picture tries to illustrate. Jaco introduced a very useful tool that he called tubular families. These are local coordinates adapted to the dynamics of the system, which he was able to use to produce conjugacies to prove structural stability. It turns out that this was a very flexible kind of approach that was later used by Wellington de Mello, for example, in his thesis, outside of the Morse-Mill setting. So Jaco was not only proving a theorem, but introducing a whole technique, a whole machinery for proving these theorems. In 2 dimensions, you can draw pictures and convince yourself that this is going to work. In higher dimensions, with critical elements of different indices, the whole picture becomes very messy, and Jaco liked to say that the experts at the time believed it was impossible to make these tubular families being compatible, but he didn't believe them, so he went on and proved that they were compatible and proved the theorem. He has a paper alone doing the 2 and 3 dimensions, and then a joint paper with Steve Smale doing the general case. So at that point, it was known that Morse-Mill are not dense, so it was known that that part of the conjecture is false, except in the context of except for vector fields on surfaces. It was also known that structurally stable systems need not be Morse-Mill. So the class of Morse-Mill systems was a first attempt at capturing the idea of structural stability, but it was too limited. And it was known that structurally stable systems are not dense either. Counterexamples, various forms of counterexamples to that formulation of Smale started to appear. So because of that, a few years later, 1967, Smale generalized the notion of Morse-Smale system, introduced what was called the axiom A class of systems, which are characterized by these 2 conditions. The non-wandering set should be hyperbolic. A point is non-wandering if every neighborhood of the point comes back to intersect itself. That's the notion of non-wandering. The point itself may go away, but someone in the neighborhood comes back to intersect to the neighborhood. So this this non-wandering set should be hyperbolic, and the periodic points should form a dense subset of the non-wandering set. So this is an attempt at generalizing what Morse-Smale is, because it was already known that the notion of Morse-Smale was too narrow to correspond to structural stability. The aim was still trying to prove that structural stability, to characterize structural stability. And so together with the 2 of them, Jaco and Steve, in 1970, formulated what was called the stability conjectures. There are 2 conjectures. First of all, a dynamical system is structurally stable if and only if it satisfies the axiom A and a condition called Strong's transversality. It's a condition about how the stable and unstable manifolds of fixed points or periodic points intersect. So this first conjecture would be the first mathematical characterization of what a structurally stable system is. What is the mathematical content of structural stability. And then there was a second version, which characterized omega stability. A system is omega stable if and only if it satisfies the axiom A and another additional minor condition called the no cycles condition. Omega stability is the same as structural stability, but you only ask the conjugacy on the non-wandering set. The idea being that the dynamics on the wandering set is trivial anyway. You focus on the hard part, which is the non-wandering set, and you ask for conjugacy to exist there. So it's analogous to structural stability with conjugacies restricted to the non-wandering set, and it's a weaker condition. If you have a conjugacy defined on the whole manifold, and then of course you have a conjugacy restricted to the omega, to the non-wandering set. So, in a sense, the stability conjectures of Palis and Smale were, at least from a certain point of view, the main challenge in dynamics for some 15, 20 years, to which many people contributed. The less difficult part was to go from hyperbolicity, axiom A, to stability, and that was done by these people. Robin, DeMello, and Robinson proved that if you have axiom A and strong transversality, then you have structural stability. This was Wellington's thesis in 1973, where he used the idea of tubular families to obtain this result. And concerning the omega stability conjecture, Smale and then Pugh and Shube proved that axiom A plus no cycles implies omega stability. So if you have axiom A, if you have a hyperbolicity, you get structural stability. That's the direction of these earlier results. For structural stability and omega stability for discrete time systems and continuous time systems. Then came a preparation for proving the converse, and it was clear from the beginning that the converse was going to be harder, because in the converse you go from stability to hyperbolicity, and stability is a strange condition to use as a hypothesis in the theorem. What was first achieved by Robinson and by Jacob was to get rid of the minor condition that comes with the conjecture. So they proved that axiom A plus structural stability gives you strong transversality, and axiom A plus omega stability gives you no cycles. So this either strong transversality or no cycles conditions are fairly easy to obtain. You should not be worried about that. The main point is not that. The main point is to prove that stability implies axiom A. This was the core of the stability conjectures, and that was all that was left to prove after this preparation. And that was the big achievement that was essentially due to Ricardo Magnier, to whom this auditorium is dedicated. In 1988, he proved that structural stability implies axiom A. And it's quite curious. Magnier passed away in 1995, and then I was asked by the Brazilian Academy of Sciences to give a lecture on his work, so I had to study it. And I realized it's very impressive. You look at his mathematical contribution up to that point, and it is like it was planned to get there. He started in his thesis. His thesis contains a little bit of this. And then there's a very impressive sense of direction pointing to this moment where he proved the stability conjecture for diffeomorphisms. This was published in Publication Mathématique de l'HOS in a big, thick volume that has only two papers, Magnier's paper and Jacob's paper, extending the argument to prove that omega stability implies axiom A. It's a shorter paper. He uses Magnier's ideas, and he finished the proof. And then a few years later, Shuhei Hayashi extended the arguments, and this was a non-trivial extension, extended the argument to flows, to continuous time. They had done the diffeomorphism case. So I don't know how much of this sense of direction that I see in Magnier's scientific evolution from his thesis to proving this result is due to Jacob, how much is due to him, but it's still very impressive. Bifurcation theory. A little bit after coming back to Rio, Jacob started to bring his colleagues and friends to visit the big conference that was organized in Salvador in 1971. Was a starting point. It's the moment where Brazil entered the map of mathematics and of dynamical systems. It was organized by Jacob, Mauricio Peixoto, and Manfredo do Carmo. And among the first visitors was Sheldon Newhouse, who was, I think, a postdoc here for a couple of years. And with Jacob, they started to think of, so, okay, we already know a little bit about structurally stable systems, but how can we go beyond structural stability? How can we say things about systems that are not structurally stable? And their first approach was, let's start within the realm of the domain of structurally stable systems, in this case, Morse-Smale. Let's start comfortably there and start moving the dynamical system by changing parameters so that at some point we cross the boundary. So we have a curve in the space of dynamical systems which starts in the structurally stable domain, but then gets out of that domain. There's a first moment, this would be CB, B stands for bifurcation, the first time you cross the boundary. And let's try to say something about what happens afterwards. This may look like a very limited objective, but this was a way to expand our knowledge from the structurally stable domain to outside of it. So that's these were in informal terms. The two questions. The moment you cross the boundary of structural stability, how does the dynamics look like? What are the ways you can break structural stability? And what happens immediately afterwards for typical values of the parameter along this curve? This is a curve in the space of dynamical systems. So they wrote, and then at some point Floris Takens joined in. They wrote several papers. There's a big one, which I like very much, this NPT in Publication de l'IHES, where they define structural stability for families, for curves of systems. They characterize the families that are structurally stable, and they prove structural stability is dense. They prove a kind of Peixoto theorem for curves of systems. Structural stability is dense amongst parameterized families of gradient vector fields. The main tool for these are fairly big papers. The main tool for proving these sorts of things, tubular families, as had been introduced in Jacob's thesis. Then, and this is more or less the time when I started being a student here. Lorenzo arrived a few months earlier. At that point, Jacob started to want to generalize this, essentially by replacing instead of starting inside Morse-Smale, let's start inside axiom A and do the same kind of, pose the same kind of questions. When the first time you stop being a Morse-Smale by moving along a curve, what is the structure of the dynamics, and what happens immediately afterwards. So these are the main, essentially the same questions, but now instead starting inside axiom A rather than Morse-Smale, and then asking the same questions as before. And that turned out to be much richer and much nicer, even nicer if you want, because it involved looking at geometrically very complicated pictures. A typical example, kind of example to keep in mind, is that you have a horseshoe, and by deforming the diffeomorphism by the diffeomorphism in such a way that you change some of the stable or unstable leaves of the horseshoe up to the point where you create a tangency between, say, an unstable leaf, an unstable manifold. In this case, it's the unstable manifold of the fixed point, of the saddle point here. You deform the picture until you create such a tangency. The tangency happens outside of the horseshoe, but of course it is affected by the horseshoe because all these stable and unstable manifolds that go through the points of the horseshoe are affected by the deformation. So if you zoom in of what is happening here, if you zoom in here, what you see is the stable manifold of P touching the unstable manifold of P, creating a homoclinic tangency, but then there are the other stable and unstable manifolds of the other points. And whether the resulting system is structurally stable or is axiom A will depend on how these different manifolds position with respect to each other. If at some point in the process of deforming another tangency is created, which is kind of to be expected, you see these curves moving, sliding in the horizontal direction, they will intersect each other. When that happens, the system cannot be hyperbolic. So understanding axiom A, understanding hyperbolicity, understanding structural stability turned out to be a problem of understanding how manifolds, dynamically defined manifolds, moving are positioned with respect to each other, whether they are tangent, close to being tangent, or sufficiently far away from tangency that you can prove hyperbolicity. So this started a whole new game called the theory of homoclinic tangencies, devoted to understanding this sort of problems. And again, Jaco's intuition was that somehow the geometry of these foliations should be relevant for stating theorems and proving theorems. Together with, there was an inspiration here, which was Sheldon Newhouse's thesis and the sequence of papers that he published afterwards. Sheldon had shown that if these families of manifolds which are moving are thick enough in some precise sense, if they are thick enough, you may fall into a situation, although this is a kind of a Cantor set of curves and this is a kind of Cantor set of curves, if these Cantor sets are thick enough, it may happen that these foliations keep intersecting tangentially at every parameter. This may happen. That's called persistent tangencies. If the invariant foliations are sufficiently thick, the existence of a homoclinic tangency may be an open phenomenon that happens that you cannot get rid of by small perturbations. In a paper that I wrote with Jaco in 1994, we extended Sheldon's theorem to an arbitrary dimension. The original theorem was for surfaces, but we could prove it in any dimension. And this inspired Jaco, as I said, to understand that the geometry of these foliations was dynamically significant. It was important for characterizing the dynamics. And then he went around trying to understand how you characterize geometry of these kind of objects, and he bumped into the notion of a fractal dimension, specifically a Hausdorff dimension. There are two numbers here, the stable Hausdorff dimension and the unstable Hausdorff dimension. Each one of them measures how thick these foliations are, and it is a theorem that the sum of these two numbers is the Hausdorff dimension of the horseshoe itself. So the whole theory was born starting from here. First type of theorems said, these are for surfaces, and there were afterwards extensions to higher dimensions by Neptali Romero and other people. The first theorem by Flores and Jaco was, if the fractal dimension of the horseshoe is smaller than 1, then you have this conclusion, which I can read in words by saying, for most parameters after the bifurcation, for most parameters after you cross the boundary of axiom A, in fact, you are axiom A. So the parameters after the bifurcation for which the system is again axiom A prevails in the sense of Lebesgue density. The relative measure of these parameters is close to 1. And about 10 years later, together with Jean-Christophe, Jacob proved that the converse is also kind of true. If the dimension of the horseshoe is bigger than 1, then axiom A does not prevail after the bifurcation. If the dimension of a horseshoe is bigger than 1, then it's not true that most parameters are axiom A, correspond to axiom A dynamics. So the precise statements are here. The short version is, in the first case, axiom A prevails, and in the second one, it does not. Especially behind the second theorem, there were in fact results from number theory. In most especially this theorem of Maasren from 1954, which said that if you have two Cantor sets on the real line and the sum of their dimensions is bigger than 1, then this set, which is a kind of weighted arithmetic difference, this set has positive Lebesgue measure for almost every parameter lambda. It's an exercise in a good first course in analysis that if you have the usual Cantor set and you take the arithmetic difference of the Cantor set by itself, so C minus C, you get an interval. Marston is a sophisticated, more elaborate version of that. Whenever you have two Cantor sets whose dimension is bigger, the sum of the dimensions is bigger than 1, their arithmetic difference has Lebesgue measure, positive Lebesgue measure, at least for if you add a parameter lambda and you consider typical values of lambda. So here it's just any Cantor set, not just a regular Cantor set. And this is the point where dynamics goes back to measure theory to produce results in measure theory. Inspired by what they knew in dynamics, Jacob formulated this conjecture for nice, dynamically defined Cantor sets. The difference, the arithmetic difference, either has zero measure or contains some interval. So dichotomy for how these arithmetic objects behave, the difference between two Cantor sets, two regular Cantor sets, is either of zero measure or contains some interval, not just positive measure, contains some interval. And this was the big breakthrough by Gugu and Jean-Christophe. Gugu had, Carlos Gustavo Moreira had partial results in his thesis, encouraging but partial. And then during his PhD in Paris with Jean-Christophe, his postdoc in Paris with Jean-Christophe, they proved not only a strong version of the conjecture, a strong version of this arithmetic statement, but they also extracted consequences for dynamics from it, specifically a very strong version of the theorem of Jacob and Jean-Christophe. One of the differences here is that here they could replace inf by lim sup, which makes the conclusion much stronger. But there are other improvements that come from this big arithmetic difference theorem. So there are two papers, one purely arithmetic in 2001, and the dynamics consequences of that, the consequences of that paper in dynamics came out in 2010. And this also inspired Jean-Christophe and Jacques to continuing the investigation, refining the investigation. Instead of, the times had moved. The axiom A was no longer the new kid on the block. There were other notions that started to appear as relevant, and in particular, they focused on something that I'm calling here non-uniform axiom A, and they could prove that if the dimension of the horseshoe is not much larger than 1, then this kind of non-uniform hyperbolicity actually prevails again. So refining what exactly is happening and how bad is the loss of hyperbolicity after the bifurcation. Okay, I move to the third and final part, which I think Jaco was elaborating during some time, but he formulated, as far as I remember, for the first time in a structured way during the School of Dynamical Systems of 1995 at ICTP. He stated various conjectures. The first version of the first paper was published in Asterisk. And so, as I said, he formulated various conjectures, but there was one essential idea, which was very typical of his. He had at that point been studying homoclinic type phenomena for quite some years. He understood that they were very complicated, that they brought a lot of richness in dynamics, and he pretty much formulated the conjecture that that's all there is. That all the problems, all the difficulties in dynamics come from that sort of configuration. So every dynamical system can be, this is a mild way of saying it, is approximated by another one which is either hyperbolic, either axiom A, either a classical type of structurally stable system, or one which has a homoclinic tangency, or a closely related, although different kind of phenomenon, which is a heterodimensional cycle. That's a kind of homoclinic tangency where there are two different points, two different saddles involved, and there are tangencies, but the tangencies occur for lack of dimension. In this example, this point here has a two-dimensional stable manifold. This other one also has a two-dimensional unstable manifold, and those two-dimensional manifolds intersect transversely. But then the other manifolds in this pair, which are the unstable of O1 and the stable of O2, also intersect non-transversely because they lack the dimension to intersect transversely. So that's what makes this kind of cycles different, ideologically different from homoclinic tangencies, but it still belongs to the same family of systems. So in 2000, Enrique Pujals and Martin Sambarino proved that any diffeomorphism of a compact surface is CR approximated by another, which is either axiom A or has a homoclinic tangency. So this was just the statement of Jaco's conjecture on surfaces. On surfaces, it makes no sense to speak of heterodimensional cycles. So the statement reduces to this, and that's exactly what they proved. Conjecture is completely true in 2 dimensions. 10 years later, Sylvain Crovisier proved that any diffeomorphism of a compact manifold is C1 approximated by a Morse-Male diffeomorphism or by a diffeomorphism having a transverse homoclinic intersection. So another statement in the family of facts covered by Jaco's conjecture. There's a subtle point that is this statement is proven only for the C1 topology, whereas Pujals and Sambarino is for CR topology. Sylvain and Enrique joined efforts, and in 2015 they proved that any diffeomorphism of a compact manifold can be C1 approximated by one that is axiom A, or by a diffeomorphism with a homoclinic tangency or a heterodimensional cycle. The difference from this and Jacob's conjecture, there are two differences. The first one is that the approximation is again proven only for C1 topology, and the second one is a very smart weakening of the axiom A condition. Essentially, axiom A means that the diffeomorphism has a finite number of hyperbolic attractors, and their basins cover an open-ended subset of the manifold. So essentially, you get rid of garbage that may live on small places, and the vast majority of your manifold belongs in the basin of attraction of one of finitely many attractors, and that's axiom A. And so with this weakening of the conclusion, they could prove essentially Jacob's conjecture in dimension 1. In the topology, in the C1 topology. Another point, another ideology in Jacob's proposal was that typical systems, this is perhaps the most famous conjecture, typical systems should have finitely many attractors. The attractors define where the asymptotic behavior is, and he believed that although Newhouse had shown that systems may have infinitely many attractors in some persistent ways, that should not be typical. So this is the statement of the conjecture. There's a dense subset of dynamical systems. Those dynamical systems have only finitely many attractors. And besides, these attractors are nice attractors with nice properties, in particular, with each one of them supporting a physical measure, mu. A physical measure is just a measure that describes the behavior, the asymptotic behavior of many points. And so almost every point should have, according to this, as a consequence of this conjecture, almost every point should have their dynamical, their asymptotic behavior defined by one of finitely many physical measures. Again, this conjecture was completely proven in dimension 1 by, in a strong form, by Arthur Avila, Wellington, De Mello, and Misha Ljubich in 2003. They proved this statement for non-trivial, in any non-trivial real analytic family of quasi-quadratic maps. Almost every map is either regular, which means that it has periodic attractors and they bring in almost every orbit, or they are stochastic, which means that they have an absolutely continuous physical measure. So it's a specific statement for dimension 1, which was explicitly motivated by Jacob's conjecture. Ljubich spoke about that here in this auditorium many years ago, and this was kind of their answer to Jacob's conjecture. With Christian Bonatti and then José Alves, we also started around that time a program for understanding the physical measures of partially hyperbolic diffeomorphisms, and we proved several results about existence and finiteness of such physical measures. And in 2005, Tsuji, and this was really a tour de force, he used some of our ideas plus new ideas of his to prove that for generic partially hyperbolic maps on any surface, it has a CR topology where R must be bigger than 22 or something like that. They have finitely many physical measures. This is actually not correct. The measures are not necessarily absolutely continuous, but that's not important. They are finitely many. They have finitely many physical measures, and they they cover indeed almost every point on the manifold, so on the surface. So again, this is one specific statement that contains Jacob's conjecture in this setting of maps on surfaces, partially hyperbolic maps on surfaces. And of course, there's a lot of things that, really a lot of things that have been done by many, many people that in one way or the other were influenced by Jacob's vision. Jacob was very vocal about his ideas. We had a very active seminar. He would keep talking about his ideas, which then became very influential for many, many people. I'm sure there are other names that I forgot that I should have included, but this is just a little bit of a hint. And I stop here. Thank you.